And I want to start out by making some announcements. So there was a question yesterday at the start of class about an upcoming test. And so I started taking a deep look at the syllabus, and so that I could gauge your next test. And my best guess is it is going to be probably next Wednesday or Friday. So I like to give, according to the syllabus, it's a week from today. But we're probably a day or so behind the syllabus. So my best guess is next Wednesday or Friday. So what I like to do is I like to give you a for sure week's notice. And it's definitely not a week from today, but be prepared for the test to be at the end of next week sometime. And then the next test is not until finals week. So test 2 on lessons 6 through 11 is not on November 1st, as the syllabus states. It will be either November 2nd or 4th. Okay, so what we have left to do is cover finish lesson 10 and then cover lesson 11. Okay, I claim that lesson 11, once you get the hang of it, kind of like the binomial, is very much like a calculator section. Okay, so that is upcoming. So be prepared for a test at the end of next week, which means that next weekend we don't have math to do, which is kind of a nice way to look at it. I mean, I'm just trying to find the silver lining here. And in addition, for due dates, boy, I can't remember when lesson 9 is due, but lesson 8 is due tomorrow by midnight. Does anyone know when lesson 9? I can look it up. Oh, thank you, Sally. Lesson 9 is due Friday by midnight. And class activity 6 is due on Friday in class or by email at class time. Okay, so we are moving right along. Again, lesson 9 is literally just a calculator section. And if you've looked at class activity number 6 that I handed out and or made available on the Moodle page, you'll kind of see what it is I'm interested in you understanding. And really that example that we did at the end of class yesterday with the batteries is a good one to look at. Yeah. Of course. So if you were not here yesterday and you are in class today and want a physical copy, I have them. Every class period, my friends, I bring any activities that are open and still to be due. And I also bring any of the activities that you physically have handed in or tests that you've taken. So I always want to hand papers off to you all. So if you're here, please get them. Yeah. Number 8 on lesson 8. I would not at all mind doing that. Let me just go to my open math. Is it okay if I do my version? Yeah. Okay. What?
Oh, I just forgot to mark our lesson had started in my notes.
Last Friday at the very end of class. So I will share my screen. Okay, so your numbers are going to differ slightly from mine. This is what you're looking at? Yeah. Okay, cool. So what we have here in number 8 for lesson 8 is we are selling tickets for $8 a piece, and we'll sell 700 tickets total. There's one, holy smokes, $3,000 grand prize. There's 3 $400 prizes and 13 $10 prizes. And we want to find the expected value for our quote unquote profit. Okay. So the first thing that I would do here is I would make a probability distribution table. I'm going to stop sharing my screen at this point so that everyone, I took the important notes so that everyone can see. All right. Now, you have a choice as to how you do this problem. Some people prefer subtracting, and this is the way that I taught it in class, is I subtract the $8 that we spent on the tickets right from the get-go, okay? I had someone ask me a question on My Open Math last night, and the way they started it is they didn't subtract off the $8 from each of these winnings, but then they subtracted it off at the end. That's okay too. But just to be consistent with the way I explained it, okay, what is the best case scenario? Isn't the best case scenario that we win $3,000? Totally. But do we actually walk away with $3,000? No, because we spent $8 to begin with, correct? So what we're going to do is take the 3,000 minus the 8, and don't we have $2,992? How many tickets win that? 1 out of the total of 700. So that's my corresponding probability. The next best case scenario is that we win $400. Again, I like subtracting the amount we spent on the ticket right from the get-go. So doesn't that mean that we walked away with $392? How many tickets win that? 3 out of the 700. The next best case scenario is we win $10. But do we actually walk away with $10? No, we only walk away with $2. How many tickets win that? 13 out of the 700. Now, everyone else doesn't win a thing. But again, I always subtract off the amount spent right from the get-go. So I claim that everybody else walks away losing $8. But remember, it's a raffle. It went to a good cause, so we're not that bummed. Okay? How many tickets lost? Well, there's a total of 700 tickets. How many of them are quote unquote winners? Well, 13 plus 3 plus 1, or 17. So aren't 700 minus 17 losing tickets? And what is 700 minus 17? How about 683? Does that make sense? Okay, so then what we would do is we would take each X value and multiply it by its corresponding probability and add them up. Okay, I can show you that in a calculator if you'd like me to. So I'll turn my calculator on here. And literally, I'm going to type in what I have here. So 2992, oops, hopefully I can do it correctly. Times 1 divided by 700 plus 392 times 3 divided by 700 plus 2 times 13 divided by 700 minus 8 times 683 divided by 700. And so in this particular example, on average, there's $1.81 deficit. And that makes sense that on average, there would be a deficit, because otherwise, how in the heck are they going to give out these huge prizes? They won't have the money to do that. Now, for those of you who didn't subtract off the 8 at the beginning, in other words, did 3,000 times 1 over 700 plus 400 times 3 over 700 plus 10 times 13 over 700, and then plus 8 or plus 0 times 683 over 700, you're going to then need to subtract off the $8 at the tail end. Just $8, because that's the amount spent. But I tend to just subtract it right from the get-go so I don't forget. Is that good? Thank you for asking. All right. So yesterday, we were talking about measures of the measures of variation with the measures of center. And what we saw at the end of class, you will compare, once you look at it, to number 2 of the class activity 6. That's really what I'm aiming for you understanding, okay? So what we talked about was the whole idea that when you have the mean, that gives you the measure of center, that gives you the average as we know it, okay? And that takes into account every data value. The thing is, we saw that outlying values, either extremely large or extremely small, can have a huge impact on our data set. So what we learned is that when we compute the standard deviation, that gives you an idea as to how spread out your data is, okay? When your data is all pretty compact, you're going to have a smaller standard deviation. And when your data is compact, in other words, not extremely spread out, what you're going to find is that your mean is a pretty good indicator of what happened with the data. On the other hand, if your data is super spread out, you're going to have a fairly large standard deviation, okay? And what that large standard deviation tells you, again, is that your data is extremely spread out, and so your mean is probably not the best indicator of what your data is actually telling you. Okay, again, you can have someone have a test score of 10 and a test score of 90, and the class average is a 50. Does this tell us much about what happened in this class of 2? No, it doesn't really tell us anything. One person really knew it and one person really did not know it, right? Whereas if you have someone, for example, get a 40 and someone get a 60, again, the average is a 50, but that 50 is a lot more indicative as to what happened here. Like, people didn't know it that well in general. Okay. So we look at the standard deviation to let us know how spread out our data is, as well as then how indicative our mean is to our data set. Okay. But there's another use of the standard deviation as a tool for measurement, and that's what I want to talk about today. And that's going to lead us really a lot into what we will be doing in lesson 11 as well. So another use of the standard deviation is as a tool for measurement. Essentially, it's a way to compare things when they are measured on a different scale. Okay, so what do I mean by that? Well, let's talk about some examples here. Okay, an admissions office, say, admissions office was looking at two students. One had an SAT score of 1400 and another one had an ACT score of 30. Who scored better? Okay. I'm not a fan of any standardized tests. I just have to state my opinion right here and now. But they have been used historically for a lot of admissions to undergraduate school, to graduate school, etc. And, you know, law school, medical school, they have them all over the place. Okay, so suppose you have one person coming in with a good score on an SAT, and you have another person who's applying to come in who also has a good score, but it's on their ACT. How do you compare these two? I mean, it's hard to compare since they're scaled differently, right? Hard to compare since they are scaled differently. But these things are done all of the time. So how do we start making a way to compare things that are measured on different scales? Okay, well, our goal ultimately is to standardize the results. Now, by doing this, it's not a perfect method, but it's one that's pretty much accepted as the way that we can essentially compare apples and oranges, for lack of better terms. Okay, so the first thing we need to do in order to standardize these results is we need a base value for comparison. Okay, in other words, this person got 1400 on the SAT. Well, what if most people who took the SAT got above 1300? Is that spectacular? No. On the other hand, what if most people who took that version of the SAT got a total of 900? You know, then this person did really well. So we need some level, something to compare it to. Does that make sense? Okay. And that value that is used is the mean. Okay. So in other words, the first thing we're going to do is say, well, how good of a score is this SAT? Well, let's compare it to the average of all the people who took the SAT, and similarly of all the people who took the ACT. Now, there's two common notations that you see for the mean. One of them that we've come across is X bar. Another one that you're going to see come up is this Greek letter mu. We love our Greek letters in math. Okay? Yep, mu, just like a kitty cat. All right. So that's one thing that we're going to do. But we've also seen that the mean can be affected by outliers, right? So we also then need to take into account how spread out is our data. Because if our data is really spread out, comparing it to the mean is going to have a very different effect than if our data is not very spread out. Okay, so essentially, the next thing that we need is we need a ruler, essentially, to see how spread out the data is. Do we have that? Yeah, that's what we were talking about in class yesterday. That's our standard deviation. Now, we saw for lesson 10 online homework that you're going to use this sample standard deviation. Okay. Another notation that we saw for standard deviation was this little sigma. Remember, that's our population standard deviation. Okay. Both of these are notation that you see for your standard deviation. Again, here's our little Greek letter. That's a lowercase sigma. Okay. Well, these things are called z-scores. And there's a formula for z-scores. Do you have to memorize the formula? Absolutely not. As always, you don't have to memorize anything. You just have to know when and how to use it. Okay? So the formula for z-scores is as follows, and I'm going to talk all about it. I'm going to put it in using the Greek letters. Okay? X is our particular data value. Mu is the mean, and I'm going to use sigma for the standard deviation. Okay? Don't worry. I'm going to go through a ton of examples of how we analyze these things. Okay? I promise. I know any new formula looks funky. Okay? So essentially what we're doing is we're taking, for example, the SAT or ACT score that a student got, and we're subtracting off the mean. In other words, we're seeing how much better or worse than they did than the average score. And then what we're doing to put it all on the same scale is we're then dividing by the spread of the data. Okay? So do you all agree? If my data value is larger than the mean, I have what's called a positive z-score, right? Because if X is bigger than mu, won't X minus mu be a positive number? Similarly, if our data value is smaller than the mean, we're going to have a negative z-score. And again, the reason why that is because my numerator will then be negative. And finally, if our data value is equal to the mean, our z-score is 0. Why is that the case? Well, anything minus itself is 0. Now we're going to see that there's certain circumstances where having a negative z-score is awesome. Okay? Two things that come to mind immediately are if you're running a race Don't you want a faster time? Okay. In other words, you want your time to be less than the average. If you play golf, don't you do better if you score below par? Yeah, you want, oh, I did a golf example. Yay. We have a golfer. Cheer. Okay, so if you play golf, you want a lower score, okay? On the other hand, when you take a test, you want a high Z-score. You want to be way better than average, ideally, okay? So there's certain situations where it's good to have a negative Z-score if you want to have a low score or be the fastest. And on the other hand, there's situations where it's better to have a higher Z-score, okay? These things are used a lot, okay? So again, just so I don't throw anybody off, another way you can write this, if you don't like this Greek letter notation, is you can use X bar for the mean and little s for your standard deviation, okay? It's just more commonly used this way. Now, what we're going to see in statistics, or what you'll see in a statistics course next semester, if you're planning on taking statistics, is a lot of times we identify things by their Z-score, not their actual data value, okay? Because a lot of times what we're interested in is how much higher than the mean or how many standard deviations above the mean or below the mean something is. You know, I think about, I have a friend who is a professor over in the law school, and everything there is graded on a normal distribution, a normal curve, which is what we're going to be talking about in the next section. So they want to give, like, you know, have most of the grades be C's, and then it maybe if you're one standard deviation above the mean or below the mean, you get a B or a D respectively. If you're two standard deviations above or below, you get an A or an F. They measure things based on how you are compared to the rest of the class, okay? So just to get us familiar with this formula, and then don't worry, I'm going to show you numerous ways we're going to use it. And this is just to play, okay? So suppose there was a test in a class, example to play with. Okay, and the average is a 75 with a standard deviation of 5. And suppose Lauren took the test and had a Z-score of negative 2.1. Bummer. What was my test score? This is just a little bit to play with the formula. That's all we're doing here. This isn't kind of a very realistic problem. Now, why did I say bummer about having a negative Z-score? I want it to be higher than average, not below average. And honestly, a Z-score of a negative 2.1 to be more than 2, what we call standard deviations below the mean, is not necessarily considered very good. But that's why I put my name to it. Okay. So notice what we're going to use is this formula. I claim we were given the Z-score, we were given the mean, and we were given the standard deviation. What we want to find is what my test score was, okay? Well, what was my Z-score? Wasn't that negative 2.1? I'm looking for X. What was my mean? What was the class mean? 75. And what was the given standard deviation? 5. Okay. Now, given the fact that I have a negative z-score, in the back of my head, what I'm thinking is, oh, I scored less than average. Okay, so we should expect, once we're done with this computation, to get a value of x that's less than 75. Okay, why do I mention that? Because it's always good to check yourself. It's really easy to make typos in a calculator. So it's always good to ask yourself, is my answer reasonable? So how do we solve this for x? I'm doing this intentionally to get our algebra in gear here. Well, what's a bummer about what we're looking at here? Isn't it a bummer that we have a denominator? Ew, we don't want a denominator. How do you get rid of denominators? You multiply both sides by them. Yeah, no, thank you. You're awesome. You're awesome. I appreciate anybody even participating. Yeah, so the way you get rid of, the way you undo dividing by 5 is to multiply both sides by 5. Remember, it's legal to multiply an equation by something as long as you multiply everybody by it, okay? Well, the cool thing is these 5s cancel and I'm left with x minus 75. And 5 times negative 2.1 is negative 10.5. All right, I want to know what x is. The problem is I'm subtracting 75. How do I undo subtraction? Addition. We can add 75 to both sides. So I'm going to get 64.5. Now in my own class, this is actually okay. It's a 65, right? Rounded, it's 65. And in my class, 65 or better is a C. So even though I scored 2.1 standard deviations below the class average, I still edged out a C. All right. So what's an example of where we might see this sort of thing? Okay, well, let's suppose someone took a test in history. And suppose they got a 90 on that test. And the class average on that test was an 88. And the standard deviation in that class was a 4. Suppose someone took a test in, I don't know, economics, and they got an 80 on that test. And the class average there was a 75 with a standard deviation of 5. Okay, same student, 2 different tests, 2 different classes. Okay, so you walk away with a test score of a 90. Are you psyched? Heck yeah, you should be. You walk away with a test score of an 80. Are you psyched? Yeah, okay. Now, in general, people would be happier walking away with a 90 on a test as opposed to an 80. Would you agree with me there? Okay, so clearly the test in history has a higher raw score. Right, 90 is greater than 80. Okay, but what I want to know is relative to the classes and their averages and distributions, which score is better? This is a classic example of when we would use z-scores. Okay, clearly, again, getting a 90 is better than getting an 80 on a test. Here you only miss 10 points and here you miss 20 points. Okay, but relative to the class and the class's average and distribution, which score is better? This is where you use the z-scores, because it's a way to get them on the same ruler of measurement. Okay, so here what we would do is for our history class, we would compute our z-score. Okay, well, what was our test score? 90. What was the class average? 88. And what was the standard deviation? 4. So you get 2 over 4 or 0.5. Okay. So we did what we would call a half a standard deviation better than the mean. Okay. So yes, we rocked the test, but pretty much the whole class did. Okay. On the other hand, for our economics class, let's compute that z-score. What was our test score? 80. What was the class average? 75. And what was the standard deviation? 5. So don't we get 5 over 5, which is 1? Notice here we scored an entire standard deviation above the mean. Here we only scored a half a standard deviation above the mean. So if I was going to put these on a ruler, if you will, here is where our z is equal to 0. That's the average. I've now standardized these, okay? Here I have my history test at 0.5, and here I have my econ test at 1. So I claim that the econ test is quote unquote better. You with me there? So do you see how we essentially put those on the same scale to measure? All right. So in general, when we look at things z-score wise, okay, z equals 0 just means that's exactly where our mean is. Okay, what we're going to find is it's most typical to score close to the mean on either side. Okay, one of the things we're going to be looking at in the next section is we're going to be talking about bell curves or normal distributions. I have to put my z there. Okay, so it's pretty typical to score in here. It's less typical to score really high or really low. Okay, so what we say is it's mostly expected that we're going to score in here close to our mean. So one more example that I want to do for today is as follows. Yep. We're going to do that tomorrow. I don't know if we're going to do that tomorrow. We're not going to do it tomorrow. We're going to do it on Wednesday. Oh, no, tomorrow is Wednesday. We're going to do it on Friday. Yeah. Okay, that's so exciting. So that's called the empirical rule, or the 68, 95, 99, 7 rule. Yeah, cool. All right, and if most of you are like, what the heck are you talking about? Don't worry about it. I teach this stuff as though you've never heard of it. Okay, so Suppose I tell you that in January, in a particular town, the average temperature is 36 degrees Fahrenheit and the standard deviation is 10 degrees Fahrenheit. Suppose in that same town in the month of July, the average temperature is 74 degrees Fahrenheit and the standard deviation is 8 degrees Fahrenheit. What I want to know is in which month is a temperature of 55 degrees Fahrenheit more unusual? When we're asking about things being more unusual, what we're asking is which one is further from the mean when you take into account the standard deviation. So when you want to know about unusual, what you're asking for is which is further from 0. Okay. Okay. No, it's not the same. I wrote the problem so it wouldn't be, but I like how you're questioning it. Notice 55 in January is going to give us a positive z-score because it's higher than the average temperature, whereas 55 in July is going to give us a negative z-score because it's a lower temperature than average. So what we want to know is which one's further away. Well, we can do January. We can find the z-score. Again, the particular temperature we're looking at is 55 minus the mean divided by the standard deviation. You're going to get 19 over 10, which is 1.9. On the other hand, for July, again, my temperature is 55, but now I'm going to subtract off the average temperature in July and divide that by the standard deviation. Right? Good job. You get negative 19, but now it's over 8 because the data is less spread out. So you're going to get negative 2.375. In absolute terms, who's further away from 0, 1.9 or negative 2.375? Further away, my friend. Yep, this is further away from 0, right? There's a greater distance. There's a distance of over 2 here. There's a distance of less than 2 here. So our answer here is July is more unusual. And I also claim, just in terms of being a human and a warm-blooded animal, it would also be more of a bummer in July, right? Because when your body's used to a pretty warm temperature, when it gets pretty cold, you feel it a heck of a lot. All right, I'm not done with this. I'm going to continue this conversation tomorrow, and it's going to be really fun. Oh, absolutely, Sally. Let me write the test first, and then I totally will. It's going to be on lessons 6 through 11. But I was actually going to be writing the test this afternoon. All right, have a great day, my friends.